Crucially, this means that when read A gets blocked on the second stage of the top pipe, reads B and D are actually able to continue progressing through the bottom pipe. And depending on how clever our pipeline logic is, we may even be able to detect the fact that read C is blocked by read A on the top pipe and reissue read C down on the bottom pipe. And so that request begins propagating towards home node H4. Meanwhile, P0 issues write B, and perhaps that location is being managed by home node H3, not by home node H4. That request begins propagating towards home node H3 at the same time that the request for write A is still propagating towards home node H4. And now you can probably see the potential issue here. And this is why we have two questions here that we have to ask ourselves as software engineers. It's not just a question of whether or not two accesses can be reordered, but whether it would actually be a bad thing if those two accesses were to be reordered. If it makes no functional difference on the outcome of our program, then it's fine for the hardware to reorder those accesses. And as we saw over the previous two lessons, allowing the hardware to reorder such accesses is a good thing. Now, it's not going to take too long for the CPU to notice the pattern here. We're loading 4 bytes, skipping 12 bytes, loading 4 bytes, skipping 12 bytes. And once the CPU does notice a pattern like this, then it may begin to speculate that we're going to continue asking it to load 4 bytes, skip 12 bytes, load 4 bytes, skip 12 bytes. And as a result of that speculation, the CPU may begin to fetch these 4 bytes here ahead of time before being explicitly asked to do so by software. That is to say, before we've actually gotten as far as the corresponding load instruction in our program. There are potential performance implications to unnecessarily enforcing stricter ordering than what's actually required. So we can do better here. Although clearly we cannot do better by using a DMB LD, because a DMB LD has load any scope, which means the write to the mailbox would be permitted to freely be reordered across the barrier, and may therefore end up being observed after the write to the flag. But what we can do is use a DMB ST. If, on the other hand, P0 is one of the Linux CPUs in the left subsystem, and P1 is one of the RTOS CPUs in the same subsystem, well, now P0 and P1 are both members of a common shareability domain. Specifically, they're in the same outer shareable domain. And in that case, we can descope our barriers from the variants here that establish order across all observers in the system to these variants here, which only establish order across the subset of observers in the system that are members of the same outer shareable domain as the CPU that executes the barrier. As another example, we can take a look at the Apple XNU kernel source code running on MacBooks and iPhones. So in case you weren't already aware, Apple does regularly release a redacted bundle of the XNU source code on GitHub for review by security researchers and the like, which also proves handy for us to use for demonstration purposes. So in the XNU kernel, we have this concept of a COM page. The kernel allocates one of these COM pages per user space task and then maps it into that task's virtual address space. The idea being that the kernel can then communicate with the task at runtime via writes to that COM page. And that's what you're seeing here. So the kernel is writing some data into the COM page for the user space task to consume, and you can see on line 6 that the kernel is issuing an inner shareable AnyScope DMB-ish as part of that communication. Which means these unrelated earlier loads and stores and these later unrelated loads and stores are all being unnecessarily ordered with respect to the critical section. Ideally, we'd like to be able to do something like this, where the barriers in our lock acquire and lock release functions act as one-way barriers. So the barrier in lock acquire would have what we call acquire semantics, which prevents any memory accesses appearing after the barrier from being reordered before it, but permits any memory accesses appearing before it to be reordered after it. And conversely, we'd want the barrier in lock release to have what we call release semantics. Well, recall that the shareability of a store release and load acquire is determined by how the virtual address being accessed has been mapped in the page tables. So if that region has been mapped as inner shareable, we'll be establishing order across all observers in the same inner shareable domain. Conversely, if we've mapped the region of memory as outer shareable, then we'll be establishing order across all observers in the same outer shareable domain. Crucially, mapping a region of memory as non-cacheable means that region is implicitly treated as being outer shareable. Next question. Which of the following instructions will correctly establish order across all CPUs running the same hypervisor or operating system kernel between a load followed by a store? Answer in 5, 4, 3, 2, 1. Well, firstly, we know that all CPUs running the same hypervisor or operating system kernel in SMP are expected to be members of the same inner shareable domain, so we can rule out any of the non-shareable variants here. I like to think of this as being a bit like a funnel, where there may be various request nodes all around the system, all trying to access the same location at approximately the same time. So this funnel is quite wide at the top, collecting up all of these different accesses, but then the funnel gets narrower and narrower towards the bottom, until we can only fit through a single access at a time, meaning the accesses need to pass through this choke point, single file. And indeed, it is the home node's job to basically arbitrate between all of the different accesses that are arriving there and to choose which access should be processed first. In other words, it serializes those accesses, hence point of serialization. Now, what I want to draw your attention to with this table is the fact that it is permitted for P0 to observe its own write before either of P1 or E2. However, it is then forbidden for, say, P1 to have observed P0's write without E2 also having observed that same write, or vice versa. In other words, either all external agents that access a location coherently have observed P0's write, or none of them have. There is no in between. So if it misses in the shared L2 unified cache, the cluster logic is going to send a snoop shared to P1, asking it to provide a copy of the requested cache line if it has it. P1 responds to the cluster logic either with a copy of the requested cache line or by informing the cluster logic that it does not have a copy of the requested cache line. And in that case, the cluster logic needs to send a transaction downstream to the primary interconnect requesting a copy of that cache line. And so the question becomes, what does that transaction look like? And indeed, fast forwarding to the much more recent past in 2023 with the J release of the Amber AXI 5 protocol specification, ARM has actually entirely removed support for distinguishing between inner and outer shareable at the interconnect level. So the Amber bus architecture's transaction encodings for inner shareable and outer shareable were both renamed to just shareable, and ARM now recommends always using the 0B10 encoding, which is what used to be outer shareable. Next, P0 issues an inner shareable memory barrier transaction corresponding to the DMB. And upon receiving this memory barrier transaction, the cluster fabric looks at the encoded shareability to determine whether it can handle this barrier entirely by itself, or whether it's going to need some help from the downstream primary interconnect. It makes this decision based on whether or not it is at or beyond the corresponding domain boundary. That is to say, based on whether it is downstream of all observers in that domain, or whether there may be other observers in that domain that are downstream of the cluster fabric. To expand on that point, well then, the first ground rule dictates that these two transactions must take the same path through the interconnect fabric to reach home node H4, and the second rule then dictates that access A reaches home node H4 first, followed by the barrier transaction. Mark all previous transactions, place a block on all new transactions, and then send its own response back to the cluster fabric. Once we've aggregated all of those responses and presented a single completion response back to the cluster is able to lift its block on new transactions and sends the write no snoop corresponding to P0's write B downstream, with this transaction then propagating towards home node H4. And here's the thing. What do you think is going to happen when write B reaches home node H4 here? Well, any non-cacheable access targeting this SRAM must pass through this home node. And with that in mind, as soon as home node H4 has serialized this access, it can send the completion response back to P0 letting it know that any future access made by any observer in the entire system overlapping its write A is now guaranteed to be observed after that write A. Well, we can think of this in terms of the order in which we would like to try to handle the request. So firstly, this is a cacheable transaction, so the component will look up in its own inline caches. If we miss in our own inline caches, then this is a snooping transaction, and specifically a read shared. So we'll send corresponding snoop shared transactions to each snoopable peer. Now, if none of the snooped peers are able to return a copy of the requested cache line, we'll need to send a request downstream. And in our case, this is an inner shareable transaction, and we are downstream of all inner shareable. Now, a question I often get asked here is, why is an ISB alone not sufficient? Why do we need both the DSB and the ISB? Now, the problem with just using an ISB here is that when we reach the ISB, we'll abandon any in-flight instructions and immediately refetch and redecode them. But without the preceding DSB, who's to say that the IC IVAL has actually completed? So we may end up just immediately refetching and redecoding the same stale opcode from the L1 instruction cache before the instruction cache invalidate has done its job. Working through this then, here the herd simulator is telling us that according to the rules of the ARM architecture's weakly ordered memory model, there are a total of 4 possible results to running this program. And herd has also identified that the condition we're looking for is indeed one of those 4 possible results. So yes, it is possible for P1 to observe P0's writes to the flag without having observed P0's write to the mailbox. Well, that's not good. So what went wrong here? Well, the herd simulator can graphically represent the interactions between different memory accesses in order to help us identify what may have gone wrong. And again, I put it to you that there is no contradiction here between what you see on screen as written in the ARM and me telling you that a DMB is actually sufficient. Now, I know what you're probably thinking. Ash, how can that possibly be? Surely I'm just chatting nonsense now, right? The ARM is literally telling us we need a DSB. Well, firstly, just to reassure you that I'm not chatting nonsense, for the DMA case, you'll recall back in Lesson 7, we saw that the Linux kernel does indeed use DMBs in its generic I/O accesses, which are used when establishing order with a DMA-capable peripheral device. A great example of this is when accessing PCIe space. So now you'll have something like an AMBER-based primary interconnect, which is what the CPU itself issues its transactions to, and you'll have some kind of bridging between that AMBER-based interconnect and the PCIe-based subsystem. And the thing about PCIe is that while writes to PCIe config space typically will respect the value of the NE flag, PCIe posted writes typically will not respect the value of the NE flag. That is to say, we'll get a completion response back from the subordinate node hooked up to the AMBER-based interconnect. Question 22. True or false? A non-shareable DMB NUSH can be used to ensure that 2 accesses issued by the same CPU targeting 2 different locations within the same memory-mapped peripheral will arrive at that peripheral endpoint in program order. Answer in 5, 4, 3, 2, 1. This is true, as we also saw back in Lesson 23. Compiling the demo and running it on an M2 Max MacBook Pro, we see the value of the byte in memory has been correctly inferred as being 42. And this took about 1/10 of a second for us to infer using the default values for those tunables that we saw on the previous slide. And this is fairly reliable, so we can keep running this over and over and we'll keep seeing value 42. That said, there is still some noise every now and then, so here I ran it 1,000 times in a row, and there were 2 instances of the inferred value being wrong. So that's a greater than 99.8% accuracy for a read speed of around 10 bytes a second. But the whole point is that we can tweak those tunables to try and strike our desired balance between speed and accuracy. Okay, so what does it look like to harden a potentially exploitable Spectre Revelation gadget? Well, coming back to our example from earlier, it means adding some extra logic to our victim function after the conditional branch that validates whether the given foo ID is within range, but before we actually use the value of fooID to index into memory. Now, granted, this example here was inside a JIT interpreter, most likely running in user space, but what I'm going to do is show you how the Linux kernel deals with this, and that's with a call to this special array index nospec function that you see here. Can you spot the issue here, though? Well, let's consider the value held at this location over time from the perspective of P1 and P2. So the word began with initial value 0xAAAA. P1 then wrote value 0xBBBB to it, and that was observed by P2's first load in program order. However, P2's second load in program order then read value 0xAAAA. In effect, it's almost as if P2's second load has been reordered here before its first load, but that's not allowed. Okay, final question. A TLBI VA E1IS is broadcast to all of our observers in the same inner shareable domain as the executing CPU. That's what the IS in VA E1IS means. So which of the following barriers will wait for those other observers to have completed handling the TLBI? Answer in 5, 4, 3, 2, 1. Well, firstly, a DMB is definitely not enough. It won't even wait for TLBIs to have completed on the executing CPU, let alone on any other CPUs. Same goes for an ISB.